Welcome to this explainer. Look around the room you're sitting in right now. It looks pretty empty, right? But if we could somehow put on a pair of specialized physics goggles, we would actually see a complex three-dimensional terrain of invisible forces and energy fields all around us. They're created by the charged particles that make up, well, literally everything. Today, we're going to learn exactly how to read this invisible map and decode the hidden architecture of electromagnetism. Here is our roadmap for today. We'll be hitting 1. Potential versus potential energy. 2. Mapping equal potential surfaces. 3. Calculating field and potential. 4. Particles to continuous distributions. 5. Energy of multi-particle systems. And finally, 6. Potential of isolated conductors. Let's kick things off with Section 1. Potential versus potential energy. Okay, we absolutely have to clear up a notoriously confusing distinction right out of the gate. We need to separate electric potential, which exists in a space regardless of what's actually there, from electric potential energy, which is the actual energy of a charged particle placed inside that space. To really wrap your head around this, think about a steep mountain. The steepness, the altitude, the overall shape of that mountain, that all exists whether you are standing on it or not, right? That is exactly like electric potential, which we represent with a capital V. It's just a property of the space itself. Now, imagine dragging a massive boulder to the very top of that mountain. That boulder now has potential energy, represented by a capital U. That energy only exists because a physical thing, the boulder, is interacting with the mountain's gravitational field. It's the exact same deal in electromagnetism. If we place a charge into a space that has an electric potential, our new charge and field system suddenly has electric potential energy. And this perfectly illustrates how we measure this invisible terrain. We use volts. Using volts simply means we're looking at how many joules of energy it takes per coulomb of charge to reach a specific coordinate. Because electric potential is essentially just potential energy per unit charge, its units are joules per coulomb. That's such a foundational metric in physics that we gave it its own special name, the volt. So, think about that standard 9-volt battery sitting in your kitchen drawer. You now know exactly what that means. Every single coulomb of charge that moves from one terminal of that battery to the other is going to undergo a change in potential energy of exactly 9 joules. Moving right along to Section 2, mapping equipotential surfaces. Imagine you're hiking, but instead of trekking up or down the mountain, you're just walking perfectly horizontally along a flat ridge. It takes no extra climbing work, right? Moving a charge along these equipotential paths is exactly like that. It requires strictly zero net work. Because the potential is completely identical everywhere on that surface, the change in potential, our delta V, is just zero. And if you recall from our source material, work equals the negative charge times the change in potential. Multiply anything by zero and boom, you get zero. Oh, and to make this physically and mathematically possible, these equipotential surfaces must always intersect the electric field lines at exactly a 90-degree angle. They are perfectly, unfailingly perpendicular. So, here is a really interesting puzzle for you. If we have the tools to track the invisible electric field vectors, can we reverse engineer the underlying potential? Basically, if we know the direction and the strength of the electric push, can we figure out the exact altitude of the electric landscape we're standing in? Let's answer that in Section 3, calculating field and potential. Moving through an electric field is a lot like hiking against a strong headwind. By integrating the electric field over a specific distance, we can determine the total potential change of the terrain. I know the formula looks a little heavy, a negative line integral of the dot product of the electric field vector and the displacement vector, but don't let it scare you. Fundamentally, it's just asking a simple question. How hard did the electric field push against us and for how far? By adding up all those tiny microscopic pushes along our path, which is literally all an integral does, we calculate the total change in voltage between our starting line and our finish line. But going the other way, that's where things get really cool. We can decode the electric field straight from the potential map by taking the partial derivative. All that means is that the electric field always points directly down the steepest slope of our potential landscape. If you somehow knew the voltage at every single point in your room right now, you could calculate the exact electric field just by looking at how fast the voltage drops. The electric field is literally the negative gradient of the potential. If the voltage drops off super fast over very tiny distance, that means you're standing on a very steep electric cliff, and the resulting electric field right there is going to be incredibly strong. All right, Section 4, particles to continuous distributions. Let's build this out a bit. I cannot stress this enough. This is an absolute game changer. Because electric potential is a scalar quantity, meaning it's just a number with no direction attached, we can just add the numbers together algebraically. This quote from the text highlights exactly why physicists absolutely love calculating potential first. Think about it. If you're trying to find the net electric field from, say, 100 different particles, you are forced to do a brutal vector addition for every single one, meticulously tracking all of their x, y, and z angles. But potential? It's literally just a number. 5 volts plus 3 volts minus 2 volts is 6 volts. It is incredibly straightforward, and it saves us from an absolute mathematical nightmare. So, when we level up to complex, continuous shapes like charged lines or solid disks, we use a classic calculus trick. We just slice the shape up into tiny, microscopic pieces, find the potential of just one of those slices, and then integrate. We imagine a continuous object like a solid ring of charge as just an infinite number of tiny point charges clumped together. We use our simple, trusty point charge formula to find the potential of one tiny slice. We call that dV, and then we just sweep our integral across the entire object to sum up all those individual potentials. No messy vectors required, just pure, elegant scalar addition. Next up is Section 5, Energy of Multi-Particle Systems. Now we're zooming out. Think of this like assembling a galaxy from scratch. The total potential energy of a system is the exact amount of work an outside force would need to do to drag each individual particle in from an infinite distance away. So imagine we start with a totally empty universe. Bringing in that very first particle, it's completely free. It takes absolutely no work because there is no existing field pushing against it. But the second it arrives, it sets up an electric potential in the space around it. So bringing in particle number 2 requires actual work. Now you have 2 particles creating a combined potential field, which means dragging in a third particle is going to take even more work. It compounds. To figure out the total energy of a structure with multiple particles, you literally just lock onto every possible pair of particles, calculate their specific energy, and then add them all together. Say you have an electric dipole, just 2 opposite charges. You just calculate the energy between those 2. But if you have 3 charges, say Q1, Q2, and Q3, you have to calculate the energy between 1 and 2, the energy between 1 and 3, and then the energy between 2 and 3. Add those 3 values up, and boom, you've got the total stored energy of your entire system. By the way, if that final result is a negative number, it actually means the system wants to stay together, and you'd have to put external work in just to rip it apart. And finally, Section 6, Potential of Isolated Conductors. This is one of the most elegant concepts in electromagnetism. Because the internal electric field of a conductor in equilibrium perfectly cancels itself out to 0, moving around anywhere inside it requires 0 work. That makes the entire inside of the object a flat, uniform potential zone. Let's tie it all together. If the electric field is 0, there is absolutely no push or pull. Without a push or pull, moving a charge requires no work. And if moving a charge takes 0 work, your change in voltage is exactly 0. So if you aggressively charge up a solid metal sphere, all those charges violently repel each other and rush to the very outer surface. Inside the sphere, the electric field is totally dead. The entire inner volume sits at one single uniform electric potential. On our imaginary topographical map, an isolated conductor looks like a perfectly flat, elevated plateau. I'm going to leave you with this final, striking scenario to think about. If you are ever sitting inside a hollow metal car during a massive lightning strike, how exactly does this invisible, mathematical physics map keep you alive? Well, your car acts exactly like that metal sphere we just talked about. When the lightning hits, millions of volts of electricity distribute themselves entirely along the outer metal shell of the vehicle. Inside the cabin where you're sitting, the electric field is perfectly 0. The entire space becomes a uniform potential zone. And because there is no difference in voltage across your body inside that specific space, the electricity literally cannot flow through you. You are completely protected by the beautiful, invisible mathematics of electric potential. And that brings us to the end of our explainer. I really hope you never look at the empty space around you the exact same way again. Keep wondering, keep exploring, and I'll catch you on the next one.